this video, we will take a look at the last of the activities pertaining to governance that we can incorporate into our ML pipelines. It's called explainability. So, what is the motivation for this? Fundamentally, AI is a black box. So, which means the more complex an ML algorithm is, the less understood is the inner workings of that ML and why certain outputs were arrived at. In fact, Jeff Hinton, considered the father of modern deep learning, himself has articulated multiple times that to this date there is no mathematical proof that's available which explains why and why a deep learning network works the way it does. So the black box nature of AI is going to be there for the foreseeable future. So then the question is, how can you explain, right? And what can you do to explain the inner workings? So at the end of the day, you're going to come up with proxies. That's a given, right? Because you're not going to get a mathematical answer for why a formula was the way it is, right? So how do you arrive at these proxies in a way that's practical and also in a way that is mimicking what is really happening under the hood? So the motivation for explainability is also something that we need to understand. It's fundamentally about building trust. If you don't have trust in the AI, you're not going to get usage of AI. If you don't have usage of AI, you're not going to get the benefits of AI. So work backwards. You build in explainability fundamentally and use that as the rubric for evaluating whether AI is successful, whether AI is trustworthy. So what is explainability in the context of AI systems? So can you provide clear and concise explanations for why certain decisions were made? Like I said, ultimately it comes down to proxies because you're not going to get a scientific answer for it. And then humans need to be able to interpret this. And this in turn provides the transparency that you need for humans to trust the AI systems. So this, ability to meet both these goals, you explain the decisions and then you have a human interpret them and build trust on it. So this meeting of both these goals is basically explainability. So the benefits of explainable AI is firstly increased trust. So you've got to get decision making that AI makes to be understood and therefore to be trusted. Second is improved accountability. So here it can really help in identifying biases or errors much earlier than otherwise, because the process of explaining a decision makes you go through the rigor associated with testing for perturbations, testing for noise, testing for representative samples, etc., etc. So that gives you better control of accountability and fairness. The third is informed decision making, which means that you can have domain specific explainability also, provide more color rather than just mathematical explainability. So this could be invaluable in certain domains like the medical field. So the example I took earlier of tuberculosis detection using X-rays, it's one thing for the AI to say this X-ray shows a patient with tuberculosis, or this X-ray shows a patient who doesn't have tuberculosis. So that's a simple yes or no classifier. But if the AI can also highlight the regions in the X-ray which have resulted in it taking the right decision or taking the particular decision, that provides that much more trust is one thing, but also provides direct clues to the doctor. And the doctor can take a look at those highlighted areas and say, I agree with that. Or this looks like something more is happening than just tuberculosis, right? Etc. etc. So that informed decision making can be very valuable for certain domains. And last but not the least is risk mitigation, because you can catch the regulatory failures much more early. So what are the techniques for explaining AI? First is you use models which are fundamentally interpretable. So intrinsically these models are interpretable. The examples are decision trees, linear regression. So the catch is obviously the power of these models is lesser compared to some of the more complex models, but at least these models are interpretable. That's point one. Second is you can use post-deployment explanation tools, which means the models have been built with accuracy as the metric or standard matrices that you normally use. And then these black box models can be explained to an extent using proxies by tools like SHAP and Lime. We'll take a look at those tools in a couple of slides, right? And you can use those explanations to also arrive at per sample or per output explanations. Now, whether they are trustworthy or not, whether they provide the right level of confidence for the humans or not, depends on the domain, depends on the problem statement. But at least these tools are available. The third is you visualize, right? You plot both the inputs and outputs and you try to build an intuitive understanding of how the two are correlated. But this works great only at the global level, which means at a level of distribution of inputs and outputs together. Whereas the first two techniques are suitable both for global as well as for local per sample predictions. So let's take a look at the two tools, SHAP and Lime. Obviously, the tools, like I said, are proxies. At the end of the day, they're trying to reverse engineer why a black box did what it did. SHAP stands for Shapley Additive Explanations. Shapley is a very specific technique in game theory. So it's a game theory based explainability. So why game theory? Think of the model as a game where the rules of the game are the nature of the representation that the model has with its objective functions. The participants in the game are the features. So the features are contributing something to the game and they are playing off each other, right? Based on based on the model's inner workings. So what Shapley values represent are, the contributions of these features relative to everything else that's happening in the model. So it gives you a clue as to which feature is most contributing to a particular output, right, at a sample level. So attributes the model's predictions to each feature as though the players are actually sharing a payout. The payout here is basically the final prediction that happens from the model. So the key idea is you look at the average marginal contribution of each feature and look at how significantly it's deviated for specific samples and use that as the basis for saying that this is the specific feature that contributed the most, specific feature value, in fact, that contributed the most for this sample. So let's take a look at an example to motivate this. The model is a black box, literally, in this case. There is a base rate for prediction of a particular output. Let's say it's an output is a regression value. So the base rate itself is 0.1. You've got a bunch of variables, and in this case, there are 4 variables. Age is 65, sex or gender is female, blood pressure is 180, and BMI is 40. So this is a very specific sample, and the black box model is outputting for this specific sample the value as 0.4. So SHAP looks at what contributions exist from each of these variables or each of these features towards that output of 0.4, keeping in mind all the other model, keeping in mind that the model is a black box, and looking at the average outputs and the average feature distributions. So the explanation it will come up with would be along these lines. Age being 65 contributes the most significantly on the positive side towards a specific value, which is plus 0.4. Gender being female contributes on the negative side, which is negative 0.3. Blood pressure being 180 contributes 0.1. BMI being 40 contributes 0.1. The base rate itself is 0.1, therefore the total is 0.4. Now, what does 0.4 for age equals 65 mean? It's not weightage, because this is the value or the contribution for this feature for this particular sample. For another sample, the explainability could be different, right? So you can't treat this as weightage or you can't treat this as feature importance, but it explains why a particular sample had the specific type of output that it did from this black box model. So the pros, the theory behind this is sound because it uses game theory, completely out of band kind of approach to how models are conventionally represented. It's consistent because it provides the same kind of explainability for the same sample again and again. Provides global as well as local interpretability. Local is what we saw per sample. Global is when it aggregates into average behaviors over a bunch of samples. The cons is that It's computationally expensive for large data sets because you're computing average marginal contributions for all features, and it's complex to explain, right? Like I just said, 0.4 is not a weightage. It's in fact for another sample, it might not even be a positive contribution. It can be a negative 0.3, right? So it's hard to explain to technical stakeholders, non-technical stakeholders, I should say. Whereas for those kinds of stakeholders, maybe feature importance is a metric to start off with. LIME is another technique. This stands for local interpretable model agnostic explanations. Again, it's intended for use in scenarios where the model is a black box. So this provides local explanations by approximating a linear regression model around a very specific prediction. So it perturbs the input data around that particular sample and arrives at a specific surrogate model, which can be used for understanding what the relative coefficients of these variables are. So let's take an example. Um, let's say it's a binary classification problem. Has diabetes or does not have diabetes. So for a specific type of sample that I'm giving, and the sample has a bunch of feature values. So glucose is 1 of 4, age is 38, pregnancies is 13, blah, blah, blah. So these are all readings. The model predicts that the chance of success, rather chance of the person having diabetes is 0.72, no diabetes is 0.28. The LIME model, what it does is, in the big feature space that's possible of all the different features, all the different values, this specific sample resides somewhere in that hyperplane, right? And there's a classifier that's already trained on this, obviously. Around this specific sample, it builds a small linear regression model, looks at small perturbations to glucose, to age, to each of these features, and sees whether the class is nudged towards no diabetes or has diabetes. So the values of 0.72 and 0.28, how do they get nudged, right? And based on that, it arrives at the contributions of these specific features to the specific sample output. So it then says that because the glucose ranges from 99 to 100 and something, its contribution is 0.12 towards has diabetes. Age being 29 to 40 has a negative contribution on that scenario, which means no diabetes is preferred as the answer in this specific sample. Pregnancies, etc., etc. So all of these are, again, features which are layered on top, and small perturbations are done, assuming a linear relationship in that neighborhood, because even in the massive hyperplane, if you look small enough, it looks like neighbors are all lying on a straight line, right? That's the intuition behind LIME. So it's model agnostic, which means the hyperplane can, rather the model that's fit on the hyperplane can be a neural network, can be a support vector machine, can be a boosted tree like XGBoost, etc. It doesn't matter, because at the local level, at the sample level, it's actually building a surrogate linear model. It's fast and easy to use. It's good for individual prediction explanations, not for global explanations. The problem is that it's only locally valid, right? So it's only locally faithful. So if you test it with a different sample, then the nature of the explanation is going to be completely different. And it's sensitive to the sampling strategy. So that's the gotcha with LIME. So when do you use which? Obviously, the best approach is intrinsically interpretable models, but that you may not be, choosing often because it's not having the right power. So in which case, you resort to visualization. Visualization gives you an intuitive understanding, but it may not give you explanations the way that you might get with SHAP or LIME. So when the explanation type that you're seeking is per sample, both SHAP and LIME can definitely be suitable candidates. But if you want also a global interpretation of a bunch of samples together, then LIME is not suitable. SHAP is probably the best. If the model complexity, rather I should say, if the ability for your explainability to work across model types without the linear approximation, then obviously SHAP is better. Otherwise, LIME. Computation wise, SHAP takes more time. It's computationally more expensive. The theoretical foundations is more sound with game theory. It doesn't rely upon any approximations as much as the linear approximation that LIME does. And then the intuition that SHAP tries to arrive at is feature attribution or feature contribution to the final output. Whereas with Lime, it's actually building a surrogate model. So, and it then computes coefficients for all the features. So that's the distinction. So in our demo, we're going to be using one of the two in combination with a drift detector as well as a bias detector, so that you know how to put all of this together. So that's in our next video. Thank you.